Hello everyone, welcome back to another new video. So we have a question, and this question is taken from the Pokhara University 2019 fall and 2021 fall. So this question will be very important for your final examination. So we have a question, we have a given frame, okay. So in this question is asked over here, you can see we need to calculate a sketch of frame having both degree of freedom and degree of static external dependency 2, okay. And here you can see generate a stiffness matrix. We have to generate a stiffness matrix for this, okay. And the height and the span of the frame component should not exceed 2 meters. Use constant flexibility rigidity. So in the question we have bounded that the height and the span should not exceed 2 meter. So it means height and span, length of span should not be more than the 2 meter, okay. And we have a constant flexible rigidity. It means ei is constant in our all this member. Here is also ei, okay. You can take ei is constant, here is also ei. So it means constant flexible rigidity, okay. So solving such type of problem, we need to calculate degree of static indeterminacy in very first, okay. So for this, now let's calculate static indeterminacy. So as we know, the formula for the static indeterminacy is DSE, okay. In very first we need to calculate external indeterminacy. So for DSE we have the formula r minus 3, okay. So r means total number of unknown reaction, okay. 3 is a equilibrium equation. So r means, you can see here we have this one is, you can see this is a fixed support, so we have three reactions. So here we get 3, and this one is hinge support, so 2. 3 and 2 means total we have 5 unknown. So the value of r equals to, we have to write 5 minus 3, okay. So 5 minus 3, it means we get value of external indeterminacy, that is 2. So you can see here this DSE equals to 2 by the applying this formula r minus 3. Now you can see here we have this frame, okay. And now if we have value of DSE equals to 2, it means the given frame is indeterminate by the 2, okay. So degree of freedom equals to 2 and DSE equal to 2. So we need to apply two different redundant force. You can see here, because DSE equals to 2, so we need to apply R1 and R2 as a redundant. So in very first, let us take this frame, this frame make again here, okay. So we have two DSE, it means we have to apply this one R1 and this R2 is a redundant force at a point C of this frame, okay. So this is our primary structure, okay. And we are applying R1 and R2 as redundant. Now we need to calculate two different value, okay. You can see here, um, we need to calculate M1 and M2, okay, because we have two different redundant force R1 and R2. So in very first we need to apply this R1 equal, R1 is a 1, okay. Unit already we have to apply it a redundant R1, and again we have to apply unit load at a redundant R2. So this can be written as M1 and this can be written as M2, okay. And in the for the this value M, you can see here we have a three different system. This one is capital M. So for the capital M, we have to just remove this redundant force, that is R1 and R2, and we have to write at the equal given frame. So if we remove this R1 and R2, then our frame looks like this. You can see this one is A, B, and C. So this one is 2 and this one is 1. So after removing the redundant force, this system measured by the capital M, okay. And when we apply first redundant as a unit force, then this is M1 system. And when we apply R2 as 1, this will be second system. Okay, so now we need to make a table. Applying this R1 and R2, we need to remove all the external force. Okay, so you can see here there is no any external force in this M1 and M2 system, so we need to remove these all the forces, external forces. Now we need to make a table. Okay, and so for the table, okay, you can see here we have to just take a limit. Okay, and the flexure rigidity is constant, so ei equals to constant, or you can say in the value of ei equals to 1. Okay, so now let's make a table. So you can see we have a very first we have a two different member. First one, you can see we have a member cb. Okay, or you can say bc. This is the first member, and another one is ba. So we have two different member, you can see. First one is this member and second one is this member. So one is horizontal member and one is horizontal member, vertical member. Okay, so cb is our horizontal member, so I have shown here this one is cb, and another one is vertical member, that is ba. So we have two different member. Okay, and for the cb, let us take origin will be c. So this is the origin, our c is origin. Okay, and for ba, let us take b is the our origin. Okay, and now if you talk about the limit, then you can see in the cb, this line, this is cb. So cb is varies from 0 to 1, and this ab is varies from 0 to 2 meter. So this is our the limit. Okay, and origin and limit. After taking origin and limit, we need to calculate m1. Okay, so we have already discussed the value of this m1 system. You can see this one is m1 system. So in this case, you can see here we have to cut out a section. Okay, let us take a section over here. Okay, our origin is this is our origin. Let us take a section, this one, x distance. So we have total x distance, and load is 1, so it means x into 1, so m1 will be 1. Okay, you can see here. Okay, and for the ba section, you can see here for the ba section, we have this r1, this one. And similarly, you can see here for this BA section, this value will be 1, and for this another section, another system M2, you can see here in this M2 system, for CB force, this CB force, the moment will be 0. Okay, so this one value will be 0, and for the BA force, this one is our BA. So for this, when you take out a section, and it will be value x into 1. So for the BA M2 will be x, and as I said, or according to the question, the flexure rigidity is constant, so we need to take value of EI as a 1. So we take on 1 and 1. Okay, for CB and for B, both sections. Now we need to calculate delta 11. So it means delta 11 means integration of m1 square dx, okay, by ei. So the value of m1 we have already calculated, that is x, you can see. Okay, for the cb section, and 1 for the ba section. So we need to take this x square from limit 0 to 1. We have taken here, you can see this one first, and this one for the second. Okay, so for this x square and limit is 0 to 1, you can see here. And for this 1 square dx, we have to take the limit 0 to 2. So we have taken, and after calculating this value, we get 2.33 by ai. So this is for the delta 1. Okay, we get this value. And similarly for delta 2 we have m2. Okay, so we need to take these two value, m2, that is 0 and x. Okay, so 0 we don't need to take anything because it will be 0, and for the x we have a limit, you can see here. For the x, limit is 0 to 2. So 0 to, we have a 0 to 2. Okay, and dx by 8 value becomes 2.66. Similarly, delta 1 to me equals to delta 2 1, and its value will be integration x into dx by ei. So you can see here this value will be 2 by ei. Okay, so after calculating we get ei as a constant, and the value of this flexible rigidity or k value we can write here. Ei is a common value, so you can take out from this matrix. Okay, and we have to just put all these value in this given matrix form. Okay, so we can see here we get the value of k equal to ei in matrix form 2.33, as we have calculated this value, and 2.66 this one, and these two values are equal. You can see here delta 1 and 2 and delta 2. So if you write this in the matrix form, then it can be written as delta 1 1. This one is delta 1 1, and you can see here in this figure we have delta 1 and 2. This is delta 2 1, this is delta 2 2. So after calculating this all value, we have to just put, and finally we get this value. Okay, so in this way we can make a flexibility matrix. So I hope you can understand. Thank you very much. See you in next video. Thank you very much.